In this tutorial, we are going to talk about creating a simulation for your ZW3D design using SimLab Composer. This is a right-angle coupler that converts the rotation's axis in a 90-degree angle. When the shaft rotates, it forces the bolt attached to it to rotate as well. And since the pivot is attached by a rotating joint to the bolt component, and by a socket to the shaft at the core of the device, it is able to conduct the motion to the sleeve, and in the same pattern of connections, the sleeve is then able to transfer the motion to the other end of the coupler. Go to the App ribbon under the SimLab Composer integration plugin. The transfer tool initiates SimLab Composer and maintains a dynamic link between ZW3D and SimLab Composer, where any changes applied to the model in ZW3D can instantly be updated in SimLab Composer. Click on the Workbench's icon in SimLab Composer and select the Simulation Workbench. From the Solid Editing dialog window, you can either choose specific parts to simulate or click on Auto Detect Solids to have SimLab Composer automatically convert all the objects to solids that can be simulated by the physics engine in SimLab Composer. Once you have identified the solids in the scene, click on End Solid Creation to proceed to adding links to the design. Notice that hovering over the components with the pointer highlights them in red, indicating that those parts are solids that can be simulated. First, we need to lock the parts of the design that will not be moving in order to hold the mechanism in place. So we select the base, and from the Solid Attributes panel, we click on the lock icon to turn it into a fixed solid. Go to the Links menu where you can create different types of joints and forces and click on Revolute Joint. Adding a joint is connecting two solids together and applying a pattern of movement according to the type of the created joint. For this Revolute joint that we created, set solid 1 to be the ground, which is translated to having an external force affecting the horizontal rod. And in this case, it's the source of the motion in this joint. Set solid 2 to be the rod, and then click on one of the rod's curvatures to denote the axis of motion for the joint. From the Joint Attributes panel, click on Enable Motor and set the speed of the motor's rotation. Go to the Simulation menu and click Start to play the simulation. The first rod is revolving as intended, but you can see the other components which are not connected are still stationary. To connect the revolving rod to the bolt component, create a Revolute joint. Set solid 1 to be the rod and solid 2 to be the bolt. Determine the axis of rotation for this joint by clicking on the curvature of the bolt in the y-axis. To connect the pivot to the bolt component, create another Revolute joint. Select the parts as solids and set the axis of rotation to this joint by clicking on the curvature of the pivot on the z-axis. Play the simulation and notice how the pivot is rotating along with the rod, yet it has the ability to rotate around its axis due to connecting it using a Revolute joint. As for the socket connection where the pivot is connected to the sleeve shaft, we would require a joint that allows the shaft to slide inside the pivot without hindering the movement of the pivot. The perfect joint for this task is the Cylindrical Joint. Go to the Links menu, create a Cylindrical Joint, then set solid 1 to be the pivot and solid 2 to be the rod. Click on the rod's curvature to set the motion path for the cylindrical joint. An additional cylindrical joint is required to stabilize the sleeve on the vertical rod connected to the base. Create a cylindrical joint and set solid 1 as the sleeve and solid 2 as the vertical rod. What is left is connecting the sleeve to the remaining parts of the device, so we will use the same type of joint we created earlier in a reverse manner. A cylindrical joint to connect the sleeve to the pivot. A Revolute joint to connect the pivot to the bolt component. And another Revolute joint to connect the bolt to the rotating rod. And finally, an additional Revolute joint to connect the rod to the base of the device to hold it in place. Click Start from the Simulation menu to play the simulation. An additional feature the SimLab Composer simulation offers is creating an analysis diagram for the simulation. From the Plots panel, select Manage Curves. Click on the Add Channel icon and then select the solid of which its data needs to be analyzed. Select which property you need to display for the solid. You can either select one attribute to display in the diagram, or you can display multiple attributes for the same solid at once. Click OK and play the simulation. SimLab Composer's ability to produce numerical data and graphs for the simulation is a great feature that allows the user to better understand the simulation and enables him to easily modify the design to serve the purposes for its intended manner, which is physically accurate. Go to the Simulation menu and click on To Animation. Select the number of frames per second to display an animation and click OK. Go to the Animation Workbench and play the animation. The physical simulation has been converted to a frame-by-frame animation, which allows you to export or share your simulation as a 3D PDF or WebGL, or create a 3D rendered video for the simulation. SimLab Composer's simulation is very simple to use and can create very accurate motion and objects interactions. Using advanced mathematical and physical equations embedded within its engine, it can turn your ZW3D models into living objects that won't require traditional methods of communication to explain, but rather a simple play button.